This is going to be very high level. This is an introductory, but if you have questions and things, please ask. But I hope this will give you some good intuition about machine learning. If you have a problem hearing me at all, let me know and I can adjust this, okay? To start, I'm going to talk a little bit about how traditional software does what it does, so you can get a sense of how machines do what they do. So first of all, for traditional software development, if you're going to write a little app to do something, let's say, for example, convert inches to centimeters, it's your job to learn the relationship between the input and the output. For example, in this case, your input would be inches. You have to learn the relationship between inches and centimeters, which we happen to know is inches times 2.54. Okay, so it's your task to tell the machine what to do, and hopefully if you do well, if it's accurate, you should get centimeters. Give you another example. If you wanted to write a little app to convert the absolute value of a number, again, you have the input. It's your job to learn the relationship between the input and the output, and in this case, it would be rules. Okay, so for example, one rule might be, if the number is greater than or equal to 0, the absolute value equals the number. Or the absolute value equals the number times -1. Okay, so that's typically how we would do it typically. What I want to ask you guys, how do you tell the difference between a cat and a dog? If you have to write the rules to tell the difference between a cat and a dog, someone tell me, how do you differentiate? Because 2-year-olds know it. You know it. You know it on sight. So how do you differentiate a cat from a dog? Other than a dog bites, a cat can too. Visually, if you have to write the rules, you're coding this. How do you code these rules? Tell me something that differentiates a cat from a dog. Shape of the nose, potential. Remember, this has to always be true. Always be true. You're going to have corner case, you're going to have exceptions, it has to always be true. What else? Slotted eyes. That's a very good one. I don't know if that's always true, but certainly for a cat, that's the case. That's a good one. What is it? The type of ears. That's the first thing I thought of when I thought of this problem. It's a tough problem. It's an age-old problem. And what I thought of the floppy ears would be one thing. But as I looked, there are cats with floppy ears. So that would be something you would have to code as an exception, right? There are cats that have hair like dogs. That would be an exception that you'd have to write. And there are some cats that don't have hair at all, right? All these are exceptions. If you had to code this problem, this is a difficult problem to code, okay? So for traditional software development, you take a cat, you would have to code all those rules. You have to say if this, otherwise that, if slotted eyes, if floppy ears, you'd have to code all these things. And if you do a good job, hopefully it will output cat. Okay? Let's talk about machine learning a little bit, so you can see why it's so different today. And I really want you to get how machines learn. It's so important to get this. I want you to look at these numbers. This is the input. Okay, you're a machine now. This is the input. 144, 181, 200, 317, and 800. This is the output. I'll give you guys about 30, 45 seconds. Tell me what 317 is. Someone in here is bright enough to solve this. Who said that? Someone said the right number, but I heard you. I heard you. Yes. 83. It's not that difficult of a problem. 400 minus the input. And what I want you to get is what you just did is how machines learn. That's exactly how machines learn. You give them the input, you give them the output, and it's their job to learn everything about the relationship between the input and the output. So for example, if this is the input you gave a machine, right? Examples that you gave a machine. And this is the output that you gave the machine. The machine's job is to learn the relationship. All of the information that relates the input to the output. And how do we do that? How does it learn that? How? Patterns, but how do we learn the patterns? Examples is always a good guess. Machine learning algorithms. I want to demystify this for you guys. Don't worry about what the algorithms are, but there's some algorithm that sits in between the input and the output, and its task is to learn everything about that relationship between the input and the output automatically. Okay, that's its task. which is totally different from what you had to do before. So you have this input, you have this output, some machine learning algorithm sits there and says, what is the relationship? In other words, there's the term function. It's learning of some unknown function. When you hear function, it's just a relationship between the input and the output. Okay? So it would learn 400 minus input. And we would call that a model. That's all a model is. You hear a machine learning model, all that model holds all the information that relates the input to the output, which is also an unknown function. So if you hear function, just think about relationship. So once we do that, we have a trained model, we have some machine learning model, and if we give it new input, and we've trained it well, it should be able to give us accurate output. Okay? So again, the whole of machine learning is to learn some unknown function. You give me X, I'm going to give you Y. I don't care what X is. I don't care if it's regression, if you want to pick a stock price, if it's the picture of a cat, if it's a scan of someone who has cancer, whatever it might be, you give me X, I'm going to give you Y. Okay? So I want you to see it this way. You have your data, and data, we're going to talk a lot about data because data is so important. It's magic if you have a lot of data and you do it right. You have your data, you apply some algorithm to that data. That algorithm learns some model. And again, that model holds all the information about the relationship between the input and the output. We call that a model. We now have that model and give it new data, unseen data. Right? And hopefully, if it's trained well, it should give you accurate predictions. So going back to our cat problem, the way we'd solve that problem, you guys, unless the rules are so transparent, it's much better for a machine to do. We just can't code that. That's why some of these problems have been solved recently. But if you were to solve this problem, give it a bunch of pictures of cats, just a bunch of pictures of cats, blurry cats, faraway cats, cat from behind, cat from the sides, cats sleeping, cats awake, dark cats, light cats, kittens, everything you can that you're going to expect it to do, just give it as many examples as you can and label them as cat and dog, and it will learn that function. Or in other words, the relationship between the picture of a cat and what's labeled as a cat, or a picture of you and what Facebook has labeled as you, okay? And what sits in between there is an algorithm. And it's the algorithm that learns those relationships. So machine learning is this. Instead of programming a computer, you give a computer examples. That's so key for you guys to understand. If you want to solve a problem, you better have examples. You better be collecting that data now. We're going to talk about labeled data versus not labeled data. But instead of programming a computer, you give it examples, and it learns what you want. We're going to talk about what that word learns means. Okay? So why machine learning now? Why is it such a big thing now? Part of that is the increasing availability of data. You go back 20 years ago with the internet, 20 plus, with the internet, all the data that's being collected every single day, whether it's personal data, whether it's streaming data with different things, Netflix and those types of things. So there's so much more data. Social networks about 15 years ago. So much more data. And then today, mobile computing. Everything we do is captured. Everything you do is captured. If not by someone, it's certainly by your device. The sophistication of algorithms, some of the best algorithms that we have here didn't even exist 10 years ago. Or at least weren't popularized 10 years ago, like convolutional neural networks, which we'll talk just briefly about. Okay, some of these things that do, some of the great things that we take for granted weren't even around a few years ago. And then finally, the increasing power. You know, your mobile device is more powerful even than a computer was 5 years ago. And some of the software like TensorFlow and PyTorch, some of these great things that do all the AI and deep learning stuff weren't even around then. So it's a great time if you have data. So let's talk about types of machine learning. This is key, you guys. Again, there's certain things I'm going to highlight for you that I really want you to take with you. Because if you plan on doing machine learning, or if you just want to have some good intuition to understand it, and you're thinking about maybe doing it, or if you're on a team and you don't do it, but you want to be able to be conversant about it, there's certain things, and this is one thing I really want you guys to understand, is the difference between supervised and unsupervised learning. Let's call this a playlist. This would just be data that would be in Excel. Right, just some data. We have the song, artist, genre, and whether the person likes the song or not. Okay? In machine learning, these are called features. And statistics are called independent variables or descriptors, but we call them features. And we also call the features capital X. You learn from X to predict Y. Remember that function? You put X in that function, and it's going to give you what it's learned. And we call Y the target. So X are the features. This is what I'm going to give you. And it's the target is what I want you to give back to me. And we call these the labels. These are the answer keys. And we also call this supervised learning. If you have the answer key, and you have data that says this person likes this song, this person has diabetes, these are the students who are accepted into a school. If you have that, that's supervised learning because it can supervise the algorithm. The algorithm is frantically trying to minimize its loss or minimize its error. And the way it does that is by checking itself. Sometimes initially just might be random guesses. But because it has an answer key, it can improve rapidly and effectively. So here's supervised learning. You have a bunch of features, and you have an answer key. So if you plan on doing something with data, make sure you're collecting labeled data. It's infinitely better than unsupervised learning for prediction. And unsupervised learning is I have a bunch of data. I have age, I have income, I have number of children, but I don't have anything on what they purchased or anything that I might be trying to predict. Okay, so supervised with the algorithms and everything, infinitely better than unsupervised. So if you want to do something and you're not collecting it, start collecting it, the labels that you want to be able to predict. Okay. With unsupervised, about all we can do is clustering, for the most part, in general, is clustering. And clustering says we can only group things on similarity of features. That's all the information we have, is to say what is similar on some of these features. All women over 35 who purchase this bag and live in the western United States or something. So all we can do is cluster based on certain things. And this is clustering, where we can cluster on some similarity of features. Maybe genre. That might be something we can do. Maybe decade. But unsupervised learning, we can only try to cluster in terms of similarity of features. So you want that answer key if you can. So with supervised, we're talking about regression and classification. With unsupervised, we're talking about clustering for the most part. Another thing I want to highlight is data. So pay attention to this. I want you guys to get this. It's so important for you guys. Anyone who's playing around with machine learning, or if you have a team, or you're looking to do some things, understand this about your data, okay? The best data has 3 qualities. And I mean this sincerely. This is so important, you guys, to getting the best out of your model. The best data has 3 qualities: clean, coverage, and complete. And make sure when you leave that you understand this. That's the difference between a team who does pretty well and a team that incrementally, constantly is improving their models. So again, these could be any features. This is a data set right here. This is what clean means. Under the first feature, you have gender, and there's that F. We know what F means. A machine doesn't know what F means. So you have to correct. It's going to frantically try to say there's some pattern, there's a third gender, or there's something, I have to find some other Fs. That's what it's going to do, and so you have to correct that. Somehow you have to find what is, you want to give your model the best signal that you can give it. So go through your data, and almost all data is dirty. If you're collecting it, almost all data is dirty. So that's one thing. The other thing, if you look in the second feature, you can't have missing data. You'll get an error in terms of your model. So you either have to drop that row if you have enough data, or you have to replace it with something that's reasonable, which is called imputing. It could be the mean of something, it could be the median, but you can't have missing values. And the third feature looks like the categories are 1, 2, and 3, you have a 13. That 13, did someone put a 1 and then try to change it to a 3 and made an error? Are they encoding it as 1 and 3? Or does 13 mean something totally different? That's your task with your data, so that you're giving it as the greatest signal that you can is that model's trying to learn the relationships. Okay? This is coverage. Coverage is, I think of it as the depth, how many rows you have. As much data as you can have and as much variety as you can have. If it's going to do a task, it has to have seen it before, if it's going to do some task. So make sure that it's seen in any situation that you're going to put it in. Okay? So the depth of your data is the coverage, the quantity and the variety of the examples. Let me give you an example here. Let's say this is the data. You're a machine, and you're learning this task. These could be images. This could be predicting tomorrow's weather. This could be anything. The function that you would probably learn here is what? You're going to learn that. That's what you're going to return is 2x. Okay? Let's look at this data. Same data set, but just a different slice of it. Anyone know what that is, that function? Excellent. X squared plus 1. And you have this part of the same data set. X squared, what about all of it? That shows you the difference with coverage. What is it? Nope. Close. Say it again. Excellent. That's exactly what it is. X squared modulus 2, which means if it's odd, add nothing. If it's even, add nothing. If it's odd, add 1. And so you can see, depending on the slice of the data, your model is going to learn different functions. And so it's important to give it as much of the data that you can give it. Otherwise, it's learning the right thing based on what it's seeing. Okay? And the last thing is complete. Complete is the breadth of the data, the features. Think about this. It's your data's knowledge of the world. If it doesn't see it, it assumes that it doesn't exist. If your model needs to know this about the world, it has to be a feature. If you're trying to predict, say, the failure of a part, and temperatures related to that part failing, you don't have temperature as a part of this, it's incomplete. Okay, so your features are your data's knowledge of the world. Trust me, you're going to need to know this. This is what you're telling your model. You're going to want to know this about the world for you to make your predictions. So that's what I think of it as being how many features, the breadth of your data. Okay? One other thing, just as an aside, two things that you can do. I want you guys, something I just want you to take. Two things you can do. Always get the best model that you can. Two things you can always do. Anyone know what one of them is to improve your model? Don't expect you to know, but just what do you think? Just intuitively, what do you think if you want to get a better model? You're getting 73% accuracy on whatever it is, and you want to improve it. Do what? Well, assuming it's labeled correctly. More data, more data, more data. You don't always have a choice to get more of the data. The second thing is feature engineering, and that's where domain knowledge comes in. Each of you are specialists in some area. You're bright about something. And most data scientists, that's the skill. You can teach people to code. You can learn machine learning. It's the domain knowledge to create better features. You gave me these features, but I know there's some other features or knowledge of the world that's missing. I read a paper that said if you take this feature and divide it by 2 and then take the square root of it or whatever, and I'm going to make a new feature. So more data and feature engineering are the two best things that you can do to get a great model. And that's why domain knowledge is so crucial. I can look at the same data set, but because of your domain knowledge, I can't see it the way you see it. Okay? So your data, I want you to see that, is the view through which your model sees the world. Give it good features, it'll see things clearly and know exactly what you want it to predict. You don't, it's not going to see things clearly, and it's going to be hazy in terms of its predictions. Okay? Let's talk about model training, how we train a model. It's iterative. We have some model that's learning. It's trying to reduce its error. It's trying to reduce its error. We're feeding data to it, and we're trying to reduce its error. And it makes a prediction. Because assuming it's supervised learning, it has the answer key. That's why supervised learning is so important. It has an answer key. And so it can correct itself. It can say, these are my predictions, and I see where I'm wrong. And where it sees where it's wrong, it will go back and change its internal parameters, in some instances known as weights, coefficients, but it'll go and change its internal parameters. We'll do that iteratively until it can minimize its error. And then we call that a trained model. And most of the time, you're going to do several models. Not you just do one model. You might do one model with a subset of the features, another model with all of the features, another model with one algorithm and a different algorithm. You're going to do several models. There is no one best algorithm ever. One that did well on the last problem may not do the same on the next problem. So you're going to probably do several of them. The way you evaluate your model, almost never will you use all of your data. And typically what you're going to do is split your data up. You'll have a training set, and you'll have a test set. You put your test set off to the side. You don't touch, you don't tweak your model, and do the test set, and then come back. You get one shot at your test set. And by default, it's typically a 70-30 split. And you take your training set, and your model's going to learn from your training set. But keep in mind, the goal of machine learning is for that model to generalize. In other words, when it sees data that it's never seen, such as the test set, it has to generalize. It's not how well it does on the training set. It's no good to get 100% of the training set and 64% of the test set. You'd be better off getting 83 on the training set and 81 on the test set. Would be much better. The task is for it to generalize. And if it does that well and you're happy with it, then you can deploy your model. Whatever that means on your computer, on a website, mobile device, whatever that might be. So let's walk through this. The process that we talked about. The first thing is getting the data. What data should you use? That's up to you. There's open data sets, there's proprietary, and increasingly data is becoming more proprietary and governments are becoming more open. So there's data sets out there, but data. The better you can get data, the better off you'll be. And supervised means, is it labeled? If you want to capture something you're not labeling, start labeling it, because that's what you're going to. That's how the model's going to learn, because you're labeling it. You're saying this is the picture of someone who has arthritis, or this is whatever it is that you're trying to learn. Label it so the model can learn. Okay. Second thing is preparing your data. Is it complete? Is it clean? And does it have coverage? Does it have the knowledge of the world that it's going to need to make the predictions? Which algorithm should I use? I know you guys don't know that right now, but typically what you would do is maybe choose an algorithm from each family of algorithms. Don't even worry about that right now, but you're usually going to use several algorithms and see which one works better. But everyone would make a little bit different choice there. And then what level of performance is sufficient? Who can tell me? What level of performance is sufficient? Someone tell me what level of performance is sufficient? 100 sigma. What level of performance? If you were working on something. What is it? That's exactly what it is. It's subjective. You have to make the call. If you work for a dating site, is 50% acceptable? Is that I don't know. Is that good? I don't know what people expect. If it's music recommendations, is it 75%? If you're predicting that someone has diabetes or something, is it 90% or 99%? That's subjective. A team or you have to make that call to say what is the level of performance that's sufficient. There is no number that anyone can tell you that you have to do. For certain problems, especially things that are kind of sparse like fraud, those are difficult problems because they happen maybe 1 out of 100, 1 out of 1,000 times. And then finally, make your predictions. Now, the one thing I want to highlight about this, and I want you guys to understand this, every single thing I showed you is subjective. Each one of you would do something different. Machine learning is as much art as it is science, and everybody would do it different. What data you get, someone else is going to get different data. How you clean your data, someone else is going to clean it differently. How you prepare your data, what algorithms you choose, what level of performance is sufficient, it's as much art as it is science. Okay? Let's talk a little bit and tie this together with artificial intelligence. And if anything's not clear, feel free to ask if I need to clarify some things. Machine learning is a type of artificial intelligence. There's transfer learning, there's reinforcement learning, but machine learning sits there, and it's the one you know probably best. And deep learning is a subfield of machine learning. And when you think about AI, you're probably thinking about deep learning. Okay, and deep learning is exclusively neural networks. We'll talk a little bit about that. But when we talk about AI, we typically think about human perception or machine exhibiting behaviors that we associate with humans. Perception, problem solving, learning, creativity, all those types of things is what we associate with AI. AI is most feasible when the task doesn't require much thinking. If we can do it without thinking, like face recognition and things, AI does it probably at least as well as we do. If we can do it pretty much without thinking, there are some exceptions to that, such as with robotics. Robotics are still probably a 2-year-old. It's getting a lot better, but those are exceptions. But in terms of the things that we're most familiar with in terms of vision and language understanding, and make sure that you have lots of data available. So here are some of the examples that you may be familiar with: speech recognition, music recommendations, computer vision, language translation, sentiment analysis. All those things are largely solved problems. So for example, understanding what's in an image. If you train a model well, can understand what's in an image well. Sentiment recognition. For example, we enjoyed the food and the service was great. It knows that that's a positive. It doesn't know what it means. It has no sense of the context. Couldn't respond, but it knows that that's positive and the same thing. We had to wait for an excessive amount of time and our order was wrong. It knows that that's a negative sentiment. A lot of companies and individuals do that to see how is our product being talked about. Or if you're a political candidate, you just want to know the sentiment of maybe something happened yesterday. What's the sentiment about that? Machine translation. This is big right here. Being able to take something in one language. You can see that there's a model, a function that sits in the middle and translates that to a different language, but also taking an image and being able to annotate what's going on in that image and saying this is what's going on in that image either through language or through computer vision. Okay? And the same thing here where you're giving examples of one language and another, because the two things that we think about for AI of our 5 senses, again, is hearing or understanding language, and then computer vision. And probably more than that, that gives us a sense of artificial intelligence is language. The ability for a machine to understand our language, for us to speak to it in our language versus us having to speak to it in its language. We give machines credit for that. Even, for example, when Siri first came out, wasn't always the best, but the fact that we can speak to something gives us a great sense of artificial intelligence, and things are much better now. AI performs poorly to learn a complex concept when there's a small amount of data. And I'll give you an example, which is this right here. A young physician could probably look at 10 or 15 scans and be able to tell you if someone has pneumonia just by looking at 10 or 15 examples. If that were machine learning or deep learning, they'd probably need 10,000 examples to do the same thing. They'd probably do it at the same level, but would need so many more examples to do the same thing that a human can do. AI performs poorly on new types of data. We can generalize our knowledge. We can learn something in one way and be able to transfer it to another circumstance. Here's a situation right here where you're looking at rheumatoid arthritis in some scans. On the left is a radiograph or x-rays, and on the right what are called scintigraphy scans. Humans can go between those and get it and generalize their knowledge. Machines can't do that. And more importantly, if you train a model at your facility and you go to a different facility, there's a good chance that it's not going to work the same, unless you had some of that data. Because if you look at some of the subtle things like, do the LNR mean something? We know to disregard. A machine doesn't know that. That's a feature. That's something that it might need to know. Unless you give it a bunch of examples with some left and right and some not, then after a while it would probably learn that the L and right is no signal for me. It doesn't tell me anything, and it could ignore that. Okay? So we can't talk about these things without briefly talking about neural networks. Some of you may or may not be familiar with them, but neural networks are loosely based off the human brain and how we take in impulses and we sum them to either activate something or to inhibit something. Like if you type well, those things are activated. If you haven't run in a while, you probably feel awkward running or something like that. Some things are inhibited, some things are activated. So let's look at an example of a neural network. This is called the input layer. Don't be intimidated by this. This is just whatever our features are: age, height, weight, income, children. That's just the input layer. And let's look at this. Let's say we wanted to predict whether a student who's graduated is going to get into graduate school. Just say these are some of the features. So you'd have GPA, GRE, the quality of the university that they're coming from to apply to graduate school, and have they done research or not. These are just features. That's all that input layer is, just our feature, just like you would in an Excel table, columns. Okay? But here's what I want you to get about neural networks, which are so brilliant. That's why they're state-of-the-art today, is for this reason right here. That hidden layer. It's called a hidden layer because we don't have a clue what's going on in that layer. It learns whatever it wants to learn. And we can't peek inside. It learns whatever it wants to learn. For example, all of these inputs are a weighted combination of that feature, whatever it's trying to learn. It weighs it. Based on whatever it's trying to learn, it will say, you know what, GPA is important for what I'm trying to learn. Research is not as important. It will be the same thing for a different feature. So, for example, let's say it's trying to learn is a student independent. I don't know. We don't know what it's learning. But if it is trying to learn that, those weights will be based on, again, you probably have many more features than these four, but those weights change based on whatever that node is trying to learn. Let me make one clarification. These are called neural networks or artificial neural networks. Some people, because the analogy isn't perfect, distance themselves from it a little bit. I use neuron interchangeably. Some people will use node, unit, all those types of things. So sometimes I'll say node, but typically I mean neuron. Okay? So that's learning whatever it wants to learn. Maybe it's learning inflexible. Is the person inflexible? Whatever it's learning, we don't know what it's learning, but it's learning some latent feature. In other words, some hidden feature. We don't know the feature that it thinks is important, but that node is learning that. And these features are a weighted combination of whatever it wants to learn. Okay? Same thing here. This node's going to learn something totally different, a different feature. And then a different feature, and a different feature. And they all are a weighted combination of what it's trying to learn. Okay? And then those features that are learned that we can't see will have activations and learn whatever they're going to learn, and then there'll be some weighted combination to the output layer. So whatever those latent features that we can't see, we don't know what it's learning, but the weights there is going to be a weighted combination to say this is going to help you make an accurate prediction. Those weights are constantly changing, as we said, because it's supervised. And so with the output layer, again, these are weighted combinations, and then we make our prediction. And if it has its errors, then it'll go back and make its correction like we did before with any other algorithm. And the thing is, as you add more layers, it can learn even more things. It learns features, and then features of features, and then features of features of features. It doesn't scale well, though. And keep in mind, this is a deep neural network, which is not deep learning. Deep learning is an architecture, which I'll show you guys in just a moment. But this is where it came from. But this doesn't scale well because everything is connected. Two things I want you to remember about this picture right here. It's a feed-forward network. It goes in one direction only. Okay? And everything is connected. Everything is connected to everything else. So you have to have all of these weights. So it doesn't scale very well when you have large photos or music. It doesn't scale very well, so we come up with deep learning. Okay, so but let's talk about, did you have a question, someone here? Yeah.
So you said like it goes one way, but it says it's learning consciously.
Well, it does something called backpropagation, which changes its weights, but it still feeds in one direction. It doesn't go back. And you'll see the difference right now. I'm going to give you an exception to this. So I want to differentiate this from the others, yes.
So we're only defining what the input looks like and what we want the output?
Yes, that's it. You're giving it the input, and if you're doing well, you have supervised learning, you have some labels, and it's its job. Remember what we said? It sits in the middle, and it learns some unknown function. That's its job, is learn that function. So natural language processing, this is understanding language. Now, don't be intimidated by this, but this is a recurrent neural network. And this is what's called unrolled. Each one of those gray things is the same neuron. Think of it as being the same neuron, but I'm unrolling it so that you can see it a little bit better. Here's how a recurrent neural network. And a recurrent neural network is good when it has a sense of memory or context such as language. Language has to have some sense of context because the word that comes next depends on what came before it, which is different from photos and things. So recurrent neural networks are good with sequential things, especially when I need some sense of context. So again, these X's are our inputs. The input will go in to that neuron. That neuron will do something to it, give some output. And then the next input goes in, but look what it is going back into itself. It's not just a feed forward. So that first word, let's say this was a word, that first word and the next word is going into that neuron, okay? And it'll make some output, and then it goes to the next one. Now the first two words are going into it, and then the next three words, and by the time it gets to the end, it has some context of that sentence. And it makes what's the probability of the next word is what it's trying to learn. What is the probability of what that next word is going to be? Okay, so recurrent neural networks have some sense of memory, some sense of state, some sense of context, okay, which photos and things don't need, okay? So when we talk about natural language processing, we're talking about natural language, which is a human language, something that's been around for thousands of years, not a computer language. Natural language processing, and we're talking about how do we process that so that we can understand it. There's ways that we have to process the language so that we can better understand it. Okay? NLP is the intersection largely of AI and linguistics. So let's talk about a few of the challenges. I want you guys to get a sense of how difficult some of these problems are and what we take for granted as humans. Here's some of the challenges of doing NLP, natural language processing, what the machine has to get. So first of all, there's ambiguity in language and how we speak. Certainly in English, which is the only language I know fluently. You can say if it's different in other languages. Okay? If I say, that is your computer, okay? Then I say, that isn't your computer. We know those have opposite meanings. We know that. We can get that those are two different statements. But if I say, is that your computer? Right? And then I say, isn't that your computer? Has the same meaning. Those are difficult problems for machines to solve that we just do. We get it. And I don't know, like I said, I don't know if that's true in every language, but it certainly is in this language, in English. Okay, those are difficult problems. We know that that has the same meaning. Same thing here, misheard speech. A recognized speech or recognized speech? It's the same thing. You guys do it all day, every day, singing the wrong lyrics. And you guys say, oh, is that what they're saying in that song? So that's common. And a machine has to do the same thing that we do, trying not to mishear something and interpret what we want it to do. Same thing here. This is why recurrent neural networks are so good. Without context, what word is that? Is it project or project? It's impossible to know. Impossible to know without context. That's why you need a recurrent neural network so it knows what came before it. If I know what came before it, I can give you a high probability of which meaning you have. Okay? Convolutional neural networks don't do that. And then the same thing here. We were out, and I saw you last weekend with my wife. Now, we have enough sense personally to know the person probably means, my wife and I were out last weekend and we saw you. But we say things different ways, and we filter it. Machines take most things literally, and it has to learn those subtleties. Those are difficult tasks. Same thing here is context that recurrent neural networks do well. May I have your, what do you think? Wife. That's a good one. Please. What else? May I have your husband? No, may I have your what? What? Name? Who said attention? Attention? Money. You have your money. I like that one. It depends. And what these algorithms do, because recurrent, they know may, they know I, they know have, they know your, and probably whatever context you're in, and they take just about every single word and say, what's the probability of the next word being all of those other words in the vocabulary that there might be? So in this sense, if I'm on an airplane or maybe at a school, attention would make sense. If I'm maybe out at a club, it might be number. If I'm in the context of a valet, it might be keys. So it all depends. That's why recurrent neural networks have a sense of context that we take for granted, because we know context when someone's speaking. Now, how do we encode the word so that it can do this? This is the processing part of natural language processing. Let's say sentiment classification. If you say a touching movie full of emotions with wonderful acting worth seeing a second time, you can read that and get it, but a machine needs to read it and get it. And so what a machine has to do, first of all, it pre-processes by getting rid of all punctuation. Punctuation. It's the first step. Then it makes all the letters lowercase. Then it does what's called tokenization. Each word has to stand on its own so it can get a sense of how they're related. So it has to separate each word to get a sense of its meaning. Then it has to do stop word removal, with, of, on, gets rid of all those types of words. And then finally, it does what's called lemmas, if you know what lemmas are, lemmatization. Instead of saying touching, it gets it down to touch. Instead of wonderful, it gets it down to wonderful. So just the base words is what it tries to do. And that's how most of the processing goes. Now an algorithm can make some sense of that. The way it does it, part of it called word embeddings, or embeddings in general. They don't have to be words, but some type of categorical variable that you're trying to make some sense of it and get. For example, a machine learning algorithm does not know that cat and kitten are related. They're just letters. It has no sense of that. And the way we do that is word embeddings. And word embeddings are how we relate things. We take something that is discrete and we give it some sense of it becomes a continuous vector. Don't worry about what any of that is, but I'll show you I'll give you an example. Let's say that you have these different words. A machine doesn't know what those words are. They're just words. It has no clue of what those words are. So you give it these dimensions. And so, for example, on the dimension gender, it may learn, well, woman's a negative one because it's opposite of one. It could be either way. Music has no sense of gender, so it's a low value. These are usually between 1 or a neutral value. A voice would have perhaps some sense of gender. An apple and orange wouldn't. So those would be the encodings that would be learned. Neural networks, remember those weights on the neural networks? That's what this is done. Those are the weights. You can either take that and make a prediction, or you can just take the weights and do the embeddings. And most of the time, you just take the weights and do these embeddings, and I'll show you. Same thing here if you look at age. Men and women have some sense of age. Music, not necessarily. Voice, a little bit. Apple and orange, no. In and of themselves. Let's look at another example. Audible. The only one would be music and voice for the most part that are audible. Edible, mostly only apple and orange. And then color. You have men and women, and then you have apple and orange. It's learning these through weights by putting them. A neural network learns these weights. Then at the end, don't worry about it. You take something that's called the dot product, if you know what linear algebra is, and it will give you some relationship to see how closely related they are. That's how I can learn that a cat and a kitten and a lion and a tiger are all close to each other in space. And so it can project them out. This is not what the machine sees. This is what we can see. We can visualize it in 2D space. So we know that men and women should be close to each other. So that's how a machine can know these words are related in terms of context. King and queen are very close to them and close to each other. Animals, fruit, and numbers, but also animate versus inanimate. That's how I can learn the relationships between some of the language when you're trying to do natural language processing. Let's look at speech here, how we use speech. One is text-to-speech, synthesis, where we're creating speech. And you'll see this today, and it's getting so good with audio books and things. You can have different accents and all kinds of different things that may be more pleasant, but having some text and then converting that to speech. And then the other way is speech to text, which is so valuable that you guys take for granted every day. For example, voice commands assistance uses that voice to text every single day. And how that is done, for example, if you have an Xfinity remote, say it again. Oh, if you have an Xfinity remote, an Echo or Siri, all of these are voice to text. For example, there's a wake word. It's the only way I can understand you. I assume it's not, it's listening for the wake word, but I assume it's not capturing what you're saying. We don't know that, but So you're activated by a wake word, whether that's, hey Siri, hey Alexa, okay Google, whatever, that's the wake word. Now I'm listening to you. You set that wake word, which converts, it's typically a 0 and it converts to 1. So it's the speech to text that we do. Then we have to do speech recognition. I have to understand what you're saying. Remember, recurrent neural networks, I have to understand what is the weather tomorrow. I have to understand what that means. There has to be some meaning, because people are going to ask for the weather in different ways. Is it going to be warm today? There's different ways to ask for the weather. Give me the sports scores. Call mom. Whatever it is that you're asking for it to do, it has to understand it. Then what it does is converts that speech to text. And then we're back to our natural language processing. And then from there, it has to do intent recognition. Tell the time. Play music. Change the channel. Make a call. Most of these devices may have anywhere from 25 to hundreds of intents, where you can ask it to do something and it knows how to go do that. So next, it has to do some type of intent recognition. So it's taking the word, for example, what time is it? And it has to know that that intent means time. It knows how to do time. It just has to get this word and tie it to some intent that it knows how to do. Tell me the time. How late is it? All of those has to be interpreted as the intent time, assuming it has to know how to do that intent. And the last thing is intent execution, which has nothing to do with AI. That's just software engineering. Turn the volume up, call mom, whatever those types of things are. So the pipeline is this. Wake word, hey Siri. Speech recognition, being able to convert that to text so I can recognize the intent. And the last one, which is just software engineering, is intent recognition or intent execution. Okay? Let's jump to face recognition. Remember I said most of these are architecture differences. Convolutional neural networks, so don't be intimidated. I want to just briefly say what this is so you can get it. This is just an image. And why is it three? Why does it have 3 layers? Red, green, blue. I want you to always understand that. There's some depth to the photos. A convolution is just a mathematical process just combines 2 sets of data. That's all it is. Nothing that's intimidating, just 2 sets of data. You're going to see how it does it. It does convolution. What a convolution is this. You guys get this. If I have a filter, we were talking about cats, if I have a filter and I want to recognize maybe the ear, or the hair, the fur on a cat's ear, this filter is just looking for fur on a cat's ear, just sliding across the photo, looking for fur on a cat's ear. And anywhere where there are white spots on that, what's called a feature map, we know that there's fur there. And we do the same thing, looking for eyebrows, or looking for whatever it's looking for. That's a convolution. What a pooling is, it just downsamples it like you would for a JPEG or an MP3. It makes it smaller, so we have less data. Then we do the same thing. We do another convolution, and then we downsample it. And we do that till we get to the very end. And that very end is our fully connected neural network that I showed you guys earlier. So you see the architecture is different. So you don't have to have all of these pixels fully connected. We get it small, 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 and I'll show you in a second. Then we put it in the fully connected network. So let's say we're looking at a photo and we want to recognize someone's face. This is how you see the image. That's how a machine sees the image. It's just pixel intensities. So that's why when I ask people, how would you recognize, oh, well, you look at the distance between the eyes. That's not, machines don't see it the way we do. They don't see it. There's no such thing as an eye. They're numbers. It's just math. And so if you can keep that in mind, here's a filter also known as a kernel. Okay? This is identity, means it will do nothing when you slide it over in an image. But this, give you an example, this one right here, again, let me go back for a second. These are numbers. And these kernels are just 3 by 3. It's just 3 by 3 is doing math. Item-wise, all the way over. And what that ends up, just like you would in Photoshop or an app on your phone, that happens to be edge detection. Something else might be looking, like I said, for hair, for looking at a little curly Q, whatever it's looking for, that's what convolutional neural networks do. They're just looking for some feature in the image. Same thing here. So this is a photo. A photo has width, a photo has height, and a photo has depth. Okay? This is a filter. This is the convolution process. It's a 3 by 3 filter. It's just doing the math. The 9 pixels that it's over, it multiplies itself to those pixel intensities. That's all it's doing. And if that feature's there, you'll have a bright spot there. If it's not there, it'll be dark. That's all it's doing. It's sliding over. And so this is what a convolution is doing. Just sliding a filter over a photo, and then it outputs a feature map. It's saying, it's mapping, this is where eyebrows are in that photo. Or this is where fur is in that photo, whatever. We don't know what they're looking for, but whatever it's looking for, that feature map says this is where it is. Now, we'll do more filters. I'm looking for something different. As many as we do is the depth of that convolution layer, like that. And you notice it's deeper and smaller, deeper than we downsample, which is pooling. Now, on that convolution layer, we're going to do the same thing. We have some filters that are going to learn something else. We're going to slide it over there. It's going to be deeper and smaller. And then we'll do that again there. It's going to be deeper and smaller. So think about this, what a convolution is doing. It's taking in an image and squeezing out all of the spatial information, getting it down to just the most important features. It's getting deeper and smaller, deeper and smaller, deeper and smaller. I want you to see it from here. There's a 128 by 128 image. Because it's RGB, its depth is 3. We use 64 filters. We use 40 filters. That's why its depth is 40. That's 40 feature maps. And you see its size is half. That's the pooling. And then we use 80 features on that one, and it's half because of the pooling. And then deeper and smaller till you get all the way to the end. I want you to notice this. At the very end, you have 1,024 2x2 pixels. And what we do with those, we do what's called flattening. If you look at the very end, those are flattened. If you do the math, it's 4,096 that we input into the neural network. Okay? And I said all that to say this, to get to this part. Facebook. And that is Facebook can recognize you no matter what. No matter what, and it's crazy. That's the deal you made with Facebook and most of these other companies, is by playing and having fun. There's a model of each one of you guys out there. And if it's okay with you, that's why they can tell you, hey, you're in this photo. Is this you? Tag? Or they'll say the same to someone else. Is this such and such in this photo? Because they have a model on everybody. A model on each one of you. Now, you can ask them to delete it, and they probably will. But they're going to learn it. If you're still on there, they're going to learn it again. Okay? So no matter, if you're out there, whether it's police, surveillance, whatever, they can see you. Even if it's not reported, they can see you. And that has an issue with security. And last month, this is what Facebook announced. Just last month, they, by default, by default, face recognition is off. They still have a model on you, but your friends won't get the message saying, is this such and such in this photo? And you won't be alerted to say, we think this is you in the photo. That's turned off by default. You can turn it back on. If you're a new user, if you're an old user, it's probably still on. And maybe you don't care, if that's the case. But Facebook is state-of-the-art, 98+% accuracy for face recognition. Hat, glasses, in shadow, turn to the side, it doesn't matter. Okay? Now, I want to show you the difference between machines and us. I'm going to ask you guys to do something. I want you to look at this person right here. Okay? And I'm going to ask you if the next picture is the same person. Okay? Same person or not? Who says it's the same? Who says it's different? Or we're about split in half. Same. Same person. Part of that, again, the reason I'm showing you this is because we're biased and machines aren't. Sometimes you look on the left, oh, that's not the same girl I saw. She has an attitude, and the person on the right is more affable. And so we have some of that we don't even think about sometimes when we're judging things. Let me give you guys another one. I want you to see this person here. Same or different? Same? Different. Different. We're terrible with similar-looking strangers. We have a 30% failure rate, especially when their hair is the same or if they have clothing that's the same. Machines don't have that problem. Okay. One more. Same or different? Who says different? Who says same? Same. Those are tough problems that machines don't make those mistakes that all of you guys are making. Okay. But we do have this problem with machines. With races, machines don't do as well, especially with minorities. Research shows. For white males, 99% accuracy predicting their gender. Black females, 34% more accuracy, and it has to do with models and bias and how they're trained. Same thing with the police. A lot of times if they're trained on those who are arrested, then you get biases. And so they do have their own bias in other ways that perhaps we don't have. But research does show that we recognize our race or ethnicity better than others. And part of that might be that we can keenly see others of our race and we generalize others. That's what the speculation is. But certainly machines are doing that. They need to either be trained separately by race or have greater diversity in what they're training on. Here's one thing I want to show you. Generative adversarial networks. Anyone ever hear of these? Just one person. Wow, these are exciting, you guys. This is the future. GANs can generate just about anything. Music, photos, just about anything that you can have it predict. And I want to give you an example here. Tell me which photo here was created by a computer? Bottom which? Bottom left? Right. Every picture was created by a computer. Good job. Every single of those pictures was created by a computer. Here's what general adversarial networks do. I want you to get this because it's incredible what they do. What we've been talking about are discriminative algorithms. This is a generative algorithm. I'll show you what the difference is. A discriminative algorithm takes features and predicts the label. Takes features and predicts that it's a woman or whatever it might be. What a generative does is the opposite. It takes a woman and predicts what she would look like. It's the exact opposite. Or it takes a song, classical music, and tries to generate the music itself. Those are generative adversarial networks, and that's why those were created. So here's what it does. This is why it's adversarial. The generative neural network creates these fake, whatever it is, music, photos, whatever it is, it creates them. The discriminator says fake or legit. That's its job. They're fine. It's trying to fake the discriminator out in the future. Nope, I'm not letting you fake me out. Can I tell the difference between the label data and a fake? And if it says legit and it gets fooled, then that's probably a good generative model. And that's all it does. It creates paintings. It trains on paintings. It can create Van Goghs. Anything it's trained on, it can do. And here's what happens when you get a fake. Sometimes it just makes mistakes and doesn't do very well. Okay? And if you look at the very top, this person does not exist.com. If you go there, every time you load the page, it's going to create a fake person, and you'll see it. It's amazing how real it is. I want you to see here. These are also fakes. If you look closely at the guy on the upper left, you can kind of see some flaws and things. If you look in some of the photos, you look closely, you can see it does such a great job from learning from data and then generating these things. Here's another thing. We have face apps. Maybe some of you may have heard of face app. The picture in the upper left is the real person. And it can create a person, a younger version of that person, an older version of that person, how the person would look in the opposite gender. It's amazing how it can do that. Same thing here with Obama. And this is the hot filter. I guess it's the hot Obama down here. But it's amazing how some of these things can be done. So let me show you one other thing so we don't run out of time. Some of you have probably heard of the human genome. It's the series of genes that makes us, or the set of genes that makes us. Okay? And researchers are comparing the DNA between 1.1 million people, and that's growing. Research shows that there'll be about 2 billion genomes sequenced in 10 years. In 2001, it cost $100,000 to have your genome sequenced. It costs $700 today and dropping. And the point of all that is because this has become another source of data and information to learn from. So and what they're doing with these, with comparing these, is trying to find some variability between certain traits. For example, let's say you took a bunch of tall people, right? And you want to know what makes them tall. What makes certain people tall? You take their genome, right? They're billions of letters or base pairs, and you pass them into some neural network. That neural networks learn patterns and data. And if there's something in the genome that makes someone tall, they can learn that. And what researchers have found, for example, the model might say here at location 391, there's some mutation. And then on location 3,764, there's a mutation. And then there's an outlier on location 1,653,000. It finds all of these, and researchers have shown there's about 20,000 different locations that influence height. And so now you take a new person, pass them to the model, they can very accurately predict someone's height. But the reason I say that is because of the controversial of IVF. And that is 1.5% of all kids born are through IVF today. And most people who do IVF do genetic testing, pre-implantation screening on the embryos to try to determine certain things. Most of the time it's to just make sure the quantity of the chromosomes is right, which is screening for Down syndrome. But increasingly, 9% of people are screening for gender. Certain countries like England and others, it's illegal. But here you can do it, 9% screen for gender. But research is, as we get, we're going to have 2 billion of these genomes. Research is trying to look at the relationship between these and intelligence. And so, and other things, eye color, skin color, if you want your child to be a little bit darker or lighter, hair color, all these types of things, as you have all these genomes, and machine learning can learn from these. Some people are in a position where they have to select. What if a doctor told you, embryo number 5 has a 40% chance of being less intelligent than the others? Do you select it? Embryo number 2 has a 70% chance of being taller. These are tough questions that people are going to be faced with because of these genome things. It's the same thing here. I don't know what people would choose, but those are tough problems that some people have to be faced with. Lastly, I want to say this because I love Spotify. I want to bring all this together with Spotify. How many of you have Spotify? It's always few people. More people than I thought. How many have Apple Music? Wow, that's amazing. I love Apple. I'm an Apple fan person, but man, Spotify is magic. And I do machine. It is magic, you guys. Spotify has something. It's called Discover Weekly. They offer you 30 songs every Monday that you've never heard that they think will delight you. And at first, I ignored it probably for a year or two, and I started putting, maybe I'd recognize 3. Now I probably put 67% of the songs that are given to me in a playlist. I haven't heard of any of the artists. And one thing about this that is great, most companies do what's called collaborative filtering. Netflix, Amazon, even all the music companies. Collaborative filtering is, if person A likes a song and person B likes a song, well, I'm going to recommend some of person A's songs that they play a lot to person B, if they haven't listened to them. The same thing for person B to person A. Same thing that Amazon does, Netflix, they could recommend a song to you or tell you 73% chance that you're going to like this movie. That's collaborative filtering. But what Spotify does is a couple of things. We talked about embeddings earlier. They do these embeddings. They do natural language processing to go out to blogs and music magazines to see what's called a social vector. How are things being talked about so I can see where they may fit? And so they can get a sense of what's close to something else and recommend things that way. This is what it would look like. Don't worry about the number. The same thing with neural network, where it has a song, has all these dimensions. And again, as I said, if you do a dot product, you can say song 1 obviously would be perfectly related to itself, but you can say what other songs would be related so I can recommend them. And you can visualize them. It's called T-SNE, which allows you to visualize these. So here, you can see the different genres. And they sit on top of each other. And the point is, you can say, even though this user likes jazz, there's this rap song that's very close to him or her. And I can recommend that because it's similar. But that's not even what makes Spotify so great, in my opinion. That is convolutional neural networks. If you can visualize it, convolutional neural networks can work with it. And you can visualize music with spectrograms, and that's what Spotify does that no one else does. And it's incredible because they can learn what are called latent features again. Features that you can't see, that you don't know about. And each one of you, one has a taste profile to have a sense, but also they learn the temporal acoustic features of the music. So the problem with collaborative filtering is the cold start problem. If you've never heard, if a song just came out tonight, or if a band is not popular, or if a song is unpopular, how do I recommend it to anybody? Collaborative filtering wouldn't pick up on it. That's convolutional neural networks. It has the temporal acoustic features of songs that you like, so a song can come out tonight, or a song can be very unpopular, and they still can put it in your playlist. And finally is this right here, using convolutional neural networks. If you go to Spotify, let's say you go to rap, or you go to weekend, or workout music, even though it's a playlist, it's still customized for you. If you and your friend go to that same playlist, your playlist is going to be slightly different because of convolutional neural networks. I just think that's incredible how they personalize the music for you. Anyway, I just wanted to show you how some of they do natural language processing, convolutional neural networks, and collaborative filtering to do some of the things that they do. I'll open it up for any questions for you guys before we run out of time. Any questions? Yes.